Hello viewers on YouTube. In this video tutorial, we're going to prove the derivative of cot x. So what says the derivative of cot x is said that if y is equal to f of x and f of x is equal to cotangent of x, which is the same as cot x, then the derivative, the y dx, is equal to negative cosecant CSC squared x, negative cosecant squared x, or negative cosecant x, then all squared. So the goal and the purpose of this video is to prove why this is true, is to prove and show this formula out. All right. So to begin this, first you need to understand what the cotangent function is. The cotangent function is a function that is typically the reciprocal of tan x. So 1 over tan x is what gives us cot x, and 1 over tan x gives us cosine x divided by sine x. So this is the one we are going to be making use of. We are going to replace cotangent of x with cos x over sine x. Perfect. So therefore f of x is equal to cos x over sine x. Now, to prove this out, we are going to consider using the definition of derivative, which says that if y is equal to f of x, then the y dx is equal to the limit as h approaches 0 of f of x plus h minus f of x, then entirely divided by h. So that's what we're considering using. So if f of x is cos x over sine x, then what would be f of x plus h? Well, what that means makes sense is that, let me put that here, wherever we see x in f of x, we should replace with x plus h. So therefore, f of x plus h, as we can see that, will be equals to cosine x plus h, cos of x plus h, all divided by sine of x plus h, sine x plus h. Perfect. So let's continue our proof. So therefore, we can plug in the corresponding values right in this definition of derivative formula. So therefore, the y dx is now equal to the limit as h approaches 0 of f of x plus h. We said that is cosine of x plus h by sine of x plus h. So we have cos x plus h divided by sine x plus h. Then we have minus. So f of x, we said that is cosine x over sine x. Down we have cos x divided by sine of x. Perfect. Now we still have a division of h. So we have divided by h. Good. So this is a compound fraction. We have to simplify that. So I'm keeping this and I'm changing this long division to the regular one, the most often used. So we have the y dx equals to the limit as h approaches 0 of cosine x plus h by that of sine x plus h, the minus cosine x divided by sine x. Okay, perfect. So right now, instead of the number line division, we are having the regular one. Okay, the regular division. So we have divided by that will be h. So now we can use the method of keep, change, and flip. So the method says that we should keep this first fraction, we should change this sign to product, and then flip this one. So we have the limit as h approaches 0 of cosine of x plus h divided by sine of x plus h, then minus the cosine of x divided by sine of x, then the sign change to product, then we have 1 over h. So we change this to times, we flip this one. Perfect. So therefore the y dx is now equal to the limit as h approaches 0 of cosine. So before I multiply, let me try and find the LCM of these two numbers or these two functions. Then we just try and combine them, there should be a bracket here because it's multiplying everything all through. So let's do something here. So the LCM should be sine of x plus h sine of x. So we are dividing through by sine of x plus h, then sine of x. Perfect. So sine of x plus h in this entire expression left it's sine x. Then we multiply with this. We have cosine of x plus h times sine x. Then we still have the subtraction sign connecting them. Okay, then sine x in this entire expression is sine x plus h, and it's being multiplied with cosine of x. So we have minus cosine x times sine x plus h. Perfect. Don't forget we still have times 1 over h. Okay. Now, the goal at this point is to simplify this numerator. Cosine of x plus h and sine of x plus h, we need to expand them. And to expand it, we need to use some of our trigonometric identity. And this is the one we'll be considering using. The sine of x plus h is sine x cos h plus cos x sine h. And the cosine of x plus h is cos x cos h minus sine x sine h. So those are the two substitutions we'll be considering using. Okay, for now. Good. So therefore, the limit or the derivative is now equal to the limit. Let me try and make it a little bit bigger as h approaches 0. So cosine of x plus h, and put it down in bracket. We say that will be cosine of x times cosine of h, the minus sine of x sine of h. Perfect. Then we close the bracket. Don't forget we still have sine x to be multiplying the entire expression. So we have sine x. The minus, we have cosine of x. Now the sine of x, its expansion, I'm going to put that in the bracket as well because it's not a single term. We said that will be sine x cos h, then the sine plus cos x sine of h. Perfect. Okay, don't forget we still have division of this entire expression. So we are dividing by sine of x plus h sine of x. So since this is just multiplied by 1 over h, you can bring the h down as well. Okay, now we can proceed forward. The next thing is to distribute this sine x to these entire terms within the parentheses. And similarly, we should distribute the negative cos x because this negative belongs to this cosine. So we distribute it along. So we now have equal to the limit as h approaches 0. Oops. Okay, perfect. Hope you can see that. So sine of x times cosine h, that gives us sine x cosine x cosine h. Good. Then we multiply it with this again. We have negative sine squared x sine h. Sine x times sine x gives us negative sine squared. Now minus cosine times this expression gives us minus sine x, then equals sine x, then cosine h. The minus cosine times this entire expression gives us minus cosine squared x sine h. Perfect. And we still have a division of what? Of this. That's divided by sine x plus h. Then sine x. Then again h. Okay. Now at this point you can clearly see that these cancels this. They are like terms with opposite signs. So left over is just this at the numerator. So we now have the derivative dy dx to be equal to the limit as h approaches 0 of negative sine x or sine squared x times sine h, the minus cosine squared x sine h, then entirely is divided by sine of x plus h times sine x times h. Perfect. So now let's proceed forward. So we have to move on to the next page. So I'm going to just adjust this a little bit in order to see it. So I'm just bring this down as well. Perfect. So the y dx is now equal to Now let's try and factor out, I can see that, factor out sine h as a common factor here at the numerator. So that's what I'm trying to do. Let's factor out sine h. So if I bring out sine h, I have sine, the limit is still there. Let me write the limit first. I almost forgot. The limit as h approaches 0. So bringing out sine h, let's say negative sine h. So negative sine h, because negative is here as well and negative is here. So we have sine squared x plus cosine squared x. Okay. Then we still have the division of sine x plus h, sine x times h. Perfect. Now at this point, we need to also make use of one of our identity. The most important one is that the sum of the square of cosine of a particular angle plus this plus that of the square of that same angle. Typically, the sine of that angle, the result is 1. That's simply cosine squared x plus sine squared x is equal to 1. So as we are having here to be sine squared x plus cosine squared x, we can still replace with 1 because it is addition that is connecting them. So please keep that in mind. So this is equal to, so we are good to get rid of this. We're good with that. We can just move on this way. Perfect. So therefore, by continuing, we have the y ds to be equal to the limit as h approaches 0. Now this has become 1. Left over is just sine h divided by sine x plus h, and times sine x again times h. Now this limit is such that it is with respect to h, and this is sine x here, so it's serve as a constant, even though it's not a constant. However, we can take it out of the limit. So therefore, the y ds becomes, taking 1 over sine x outside, we have left over the limit as h approaches 0 of negative sine h divided by sine x plus h, then multiply by h. You understand? I've taken the sine 1 over sine x outside. Good. Now at this point, what I would like to do is to separate this sine x plus h out, but it won't go beyond the limit. So this we have 1 over sine x, then we have the limit as h approaches 0, then I'm going to put it in a bracket, then we have 1 over sine of x plus h. So I'm trying to detach this sine x plus h from the entire expression, so multiply by negative sine h or divided by h. Good. Now since the limit of product is product of limit, so I can distribute the limit. So we have 1 over sine x, then multiply by the limit as h approaches 0 of 1 over sine x plus h, then multiply by the limit as h approaches 0 of negative sine h over h. Okay. Now we can go ahead on substituting the limits at this point. So we have 1 over sine x times 1 over sine x plus 0, which is the same thing as sine x, times, now we'll plug in the limit as h approaches 0 into these trigonometric functions. The result returns out to be equals to 1. You can confirm that by the use of your calculator, but make sure your calculator is in radian. If you do the limit, or if you tend to be plugging in a value that is very close to 0 into the sine function and keep on dividing your answer with what you are plugging in, then at the end you should be ending up having 1. So if that is the case, we have times 1. So simplifying this forward, we left over is 1 over sine x times 1 over sine x. Well, this should be minus 1, minus an h. So times minus 1. And at the end of the day, we can clearly see that this becomes negative 1 over sine squared x, which is the same as negative cosecant squared x. And this is how the derivative of cot x is being formed. And that is why the derivative, the y ds, is equal to negative cosecant squared x. I hope you find this helpful and understandable. Now you know the derivative of cotangent x. Thanks for watching. See you in the next video. Bye for now.